I want to look at a couple more examples from section 2.2. The first example, we started this one in class, but suppose we choose a real number x from the interval 2 to 10 with density function of the form f of x equals c times x, where c is some constant. The first question is to find a c, and in that we're trying to come up with a c value that's going to cause this function. So I'm going from 2 to 10, and I need my c value here to be such that the area, it's supposed to go down to 10, so it's going to pick up, it's going to be 0 on either side of that interval, and inside here we want the area to be equal to 1. So we can set up an integral from 2 to 10, or we could just use the formula for the area of a rectangle, but in general you would set up an integral of f of x, so c times x dx, and what we would like is for that to be 1. And when we take the antiderivative, we get c x squared over 2. Going from 2 to 10, we want that to be equal to 1, so we get c times 100 over 2 minus 4 over 2 equals 1. So c has to be equal to 2 over 96, or 1/48. So that's the c value that we're going to use. In part B, we want to find the probability of the event E, where E is some subinterval that looks like AB sitting inside of 2 to 10. So A is greater than or equal to 2, it's less than or equal to B, and then B is less than or equal to 10. A needs to be strictly less than B, so we actually have an interval of a certain length there. So we're just going to integrate from A to B of 1 over 48 times x dx, and so we get 1 over 48 x squared over 2 from A to B, and when we plug all that in, we're going to get 1 over 96, taking the 1/48 and the 1/2 there, putting them together, and then we'll have b squared minus a squared. So for any subinterval AB, we can find the probability that we fall inside of it by using that formula. And then finally, if I want probabilities with specific values, probability that x is greater than 5 is just going to be the probability that x is between 5 and 10. So I could set that up as an integral from 5 to 10 of 1 over 48 x dx, or I could just use the formula from the previous part and have the interval 5 to 10. Either way, you'll get 1 over 96 times 100, 10 squared, minus 25, which is 5 squared. So I get 75 over 96 as the probability there. Or we can reduce that to 25/32. The other one, probability that x is less than 7, we can set that up as integral from 2 to 7 of 1/48 x dx. Or we can use the formula from part B. We have the interval going from 2 to 7, so we get 1 over 48 times 7 squared, which is 49, minus 2 squared, which is 4. So we get 45 over 48, or 15 sixteenths there. And then for the last part, it may seem like a odd sort of probability to ask about, but I can take x squared minus 12x plus 35 and notice that that factors as x minus 5 times x minus 7. So I want that to be greater than 0. So this is going to be equal to the probability that either x is, so these could either both be positive or both be negative in order to have the product greater than 0. So I want x minus 5 greater than 0 and x minus 7 greater than 0. Or I can have x minus 5 less than 0 and x minus 7 less than 0. Now, these can't happen at the same time, so I can just find those two separately and then add the results together. X minus 7 less than 0. And rewriting that in terms of inequalities, again, we've got the probability that x is greater than 5 and x is greater than 7. Probability that x is less than 5 and x is less than 7. Well, notice in the first one, if x is greater than 5, then x is also going to be greater than 7. So it's just the probability that x is greater than 5. And in the second one, if x is less than 7, then x is also going to have to be less than 5. So we can reduce that to the probability that x is less than 7. And now I have those values. Actually got those switched up. So probability that x is greater than 5 and x is greater than 7 is going to be probability that x is just greater than 7. So in order for both of those to happen, they'll happen when x is greater than 7, and in the other one I should have x less than 5. And then we can compute this using our formula from part B. We'll get 1 over 96, and that's going to be in both of these terms. So I'm going to go ahead and factor out of everything. Greater than 7 is going to give us 10 squared, so 100 minus 7 squared, which is 49, plus x less than 5, we're going to have a 5 squared, which is 25, minus 2 squared, which is 4, and go through and simplify that. And we end up with 72 over 96, which is 0.75. So there's a 75% chance that the third one occurs. Let's look at another example using some of the ideas from this section. This is 2.2.8. We want to choose independently two numbers b and c at random from the interval 0 to 1 with uniform density. So that's equivalent to choosing a point from the unit square at random. And we want to find these probabilities. So the first one, I want to find the probability that b plus c is less than 1/2. And if I think of this as a region in the unit square, I could come over here and solve for, let's say, b in terms of c. So we would get b less than negative c plus 1/2. And looking at a unit square, if I think of this as the c-axis down here, here's 1, here's 0, 0 to 1. On my b values, we could switch those and we get the same final answer. But negative c plus 1/2, if I were to plot the line that corresponds to that, would look like this. And then for this inequality to be satisfied, we could just pick a point in each of these regions and test it to see what happens. So if I could pick a point up here, let's say I have both b and c equal to 1/2, well, then b is not going to be less than negative 1/2 plus 1/2. 1/2 is not less than 0. So I don't want the region up there, and you could test down here. If I choose 0, 0, 0 is less than negative 0 plus 1/2. So we're looking at this region right here, and the probability that b plus c is less than 1/2 is just going to be equal to the area of that little shaded region there. So I have this triangle with base and height 1/2, so I have 1/2 times the base times the height, so 1/2 cubed, which is going to be equal to 1/8. And that's the probability that that occurs. If I look at the second question, I want b times c to be less than 1/2. Again, I can rearrange this, so b less than 2 over c. Now, if I plot part of that function, if I had equality there, so considering this as b and c, it's going to look like this. So when c is equal to 1, we would get 1/2 out of this. So I'm going to have a point over here. And then when b is equal to 1, we're going to get c equal to 1/2, maybe going back to the original inequality. So we're also going to have this point. And the rest of the graph is going to have a curve, something like that. Think of the graph of 1 over x. Here we're just looking at the part of that graph that falls inside of our square here. Now I want b times c to be less than 1/2, and so that's going to correspond to the region over here. But that's a rather awkward region to find the area of. I'd have to split it up into two different pieces, something like this, and then I'd use two different integrals. I guess I'd just need one because I could figure out the other one with the formula of a rectangle. But in general, the better way of approaching this is to find the area of that orange region and then take 1 minus that. So the probability that b times c is less than 1/2 is going to be equal to 1 minus the probability that b times c is greater than 1/2. And so this is going to be equal to 1 minus the integral from 1/2 to 1 of 1 minus, so the region, the area between these two curves, so the b equals 1 line and this curve down here, is going to be 1 minus 1 over 2c, integrate with respect to c, and we end up with 1 minus, and the antiderivative is c minus 1/2 natural log of c, c going from 1/2 to 1. If we go through and plug those values in, we get 1 minus 1/2 natural log of 1, which is 0, minus 1/2 minus 1/2 natural log of 1/2. Go through and finish simplifying these values, and let me not go through all the algebra here, but we end up with a final answer of 1/2 times 1 minus natural log of 1/2, which is approximately equal to 0.8466, so about 85%, and that agrees with what we see in the picture over here, so that seems reasonable based on the black shaded area that we're looking at. If I want to find the probability that the max of b and c is less than 1/2, well, the probability that b is less than 1/2 would correspond to this region here. So for all of these points, b is less than 1/2. I'll make those the same color. And then the probability that c is less than 1/2 is going to correspond to this red shaded region here. And the probability that the max is less than 1/2 is going to be equal to the probability that both b and c are less than 1/2. Otherwise, the max would be greater. So I need probability that b is less than 1/2 and c is less than 1/2. And that's going to be equal to the area of that region that's overlapped by both of them. And you can figure that out since it's going to be 1/4 of the total area there, and we have a unit square. That probability is just 1/4 or 0.25. In the last one, b squared plus c squared less than or equal to 1/2, b squared plus c squared is going to be a circle, the equation of a circle centered at the origin with radius 1 over the square root of 2. So that's going to look something like this. I'm going to have this quarter circle region, and so I just need to find the area of that circle and then divide it by 4. So this area is going to be equal to pi times the radius of that circle squared, and then divide the whole thing by 4, and we end up with pi times 1/2 divided by 4, or pi over 8, as the probability there.